A standard computer is like a single Nobel Prize winning professor. He can solve any complex problems, but he only has two hands. An AI, however, is a stadium of 100 billion math students. They aren't geniuses, but because they all flip their hands up and down at the exact same time, they can finish a million years of homework in a single second. This is why AI doesn't use a CPU, it uses a GPU. So CPU, the central processing unit, is the professor here, and GPU, the graphics processing unit, is the stadium of 100 billion math students. AI models are built on neural networks. Ask an AI a question, billions of simultaneous math stuff starts happening, ready to do all those billions of those maths. While CPU has only 8 to 64 cores to work, GPU has thousands of cores and billions of transistors in them. Simply put, a GPU is the stadium. Inside the stadium, there are classrooms, and those are the cores. The students are the transistors, and their hands going up and down, they are the binary. Now we see nanometers units for AI chips. Let's see what nanometers they are talking about. Let's first focus on the 5 nanometers AI chips. Apparently that is the sweet spot, advanced and most reliable at the moment. And we will dig into 3 nanometers and less later. So how small is 5 nanometers? Red blood cell is about 7,000 nanometers wide, and strand of DNA is about 2.5 nanometers wide. So 2 strands of DNA together, that's 5 nanometers. So that's the scale we're talking about for these GPUs. So 5 nanometers are like the seats, the size of the seat where the students will be sitting to do the simple tasks. Smaller means more seats for 1,000 more students. And these tiny seats sit our students. They speak only one language, binary. Hand up, that's a 1. Hand down, that's a 0. So in other words, the transistor switches either 1 or 0 to function. For example, each letter is 8 bits, 1 byte long. So each letter has this different set of binary code, for example like these. To say hi, these students perform a choreographed dance for H and for I. Another example is colors. Every color on your screen is by mixing red, green, and blue, RGB. And this is the code for the red, green, white, and black. On a chip like the Maya 100 developed by Microsoft, there are 105 billion of these 5 nanometer students. Each one flips their hands up and down 2.8 billion times every single second. That is 294 quadrillion flips every second. That's a 294 with 15 zeros behind it. By flipping the switches on and off billions of times in a short amount of time, GPU can perform maths needed to understand what you are asking and respond back to you. By the way, transistors aren't flat anymore. To get to 5 nanometers, engineers had to go 3D. It's called FinFETs. Instead of a flat path, the electricity flows through a vertical fin that sticks up like a shark. So nearly 300 quadrillion decisions every single second has been made with these tiny little shark fins. To put that speed of decision making in perspective, if every person on Earth does 1 math per second, it would take the entire human race over a year to do what this chip does in 1 second. And fun fact, the very first transistor created in 1947 was measured in centimeters, and it was about 1.5 centimeters big. You could hold it in your hand. To see the scale change, you can imagine the current 5 nanometer transistor size is a single grain of sand, and the first transistor is the size of a skyscraper. So why are there so many switches needed? One switch can tell us yes or no. Billions of switches can hold so much information that it can understand languages, recognize faces, diagnose X-rays and MRI scans by comparing to millions of others, reading and comprehending a book in a few seconds. And that's what an AI can do with billions of switches all working together. By reducing the size of the seats, we can have more cores and more transistors, which makes the AI more intelligent and faster. Then why not just pack more seats so more work can be done? Sure, but we're running out of space to shrink more seats. Before, computers were huge, they were big, there were plenty of space to shrink. Now at 5 nanometers, it's extremely tight, just about 25 atoms wide. So 5 nanometer is 25 atoms wide, 3 nanometers is about 13 to 15 atoms wide, 2 nanometers is only 10 atoms wide. So the next advances of the chips to 2 nanometers will run into some problems. And the first problem we face is called the quantum tunneling. Let's say one 5 nanometer transistor has a fence to keep the electricity inside to switch from 0 to 1. But at 2 nanometers, with only 10 atoms wide, the fence becomes so thin that the electricity does not stay within the fence. So the electricity leaks or transports through the wall, confusing if it's a 0 or 1. So the analogy is the desks are so closely put together that one student holding a hand up can hit the elbow of the students next to them, forcing their hand to go up too. So it gets confused if it's 1 or 0. So this is how electricity leakage happens that can accidentally trigger the adjacent switches. And problem 2, everything in the universe vibrates slightly. When electricity flows through the 10 atoms, they can start to shake too hard, generating heat that can melt the transistor itself. GPU is a type of AI accelerator. There are types engineered specifically for AI tasks like TPU, tensor processing units, ASIC's application-specific integrated circuits, and FPGAs, field programmable gate array. So rather than GPU, the keyword is AI accelerator. In the market of early 2026, NVIDIA has Blackwell with 200 billion students. Microsoft has Maya 200, built to run agentic AI that doesn't just talk but acts. Google has the TPU, and Amazon has Trainium, and many more. So why not use 3 nanometers, which is the best at the moment? First issue is the cost. It costs a lot more to make 3 nanometer ones than the 5 nanometers. And the reliability, 3 nanometer technology is not as reliable as 5 nanometers yet due to many faulty transistors. And thirdly, the purpose of 3 nanometer technology is not required yet. 5 nanometers can do all the things that we have at the moment. So 5 nanometers is still enough to power the AI for now. But in the future, 3 nanometers will be required. So what will we see with these advancement of AI accelerators? The first thing is thinking to doing. At the moment, we're in the digital teammate phase where we mostly only talk with the AI, but with advancement, AI will be action-oriented, as in it will create Excel for you, it will book a flight for you, or it will order a meal for you. Secondly, physical robots will be much advanced in a sense that they will not just move something from A to B. With advancement, they will decide on how to organize and clean things for you personally. And thirdly, we are going to have a personal AI. So at the moment, we use one giant AI in the cloud to access AI. But with 3 nanometer chips, we will have our own very own AI on our phone. So what's next after 3 nanometers? Optical computing is one possibility. Engineers are researching how to use light instead of electricity to switch zeros and ones, which would be much faster and require much less heat. And also scientists are working on a thing called neuromorphic chips. Engineers are working together with a neuroscientist to understand the efficiency of the human brain's neurons and build one like them instead of a wafer grid. So the 3 to 5 nanometer stadium is just the beginning. If you learned a thing or two, hit the like button and subscribe. Thank you very much for watching.